Right, morning lads. Hope you're well. I have now marked everyone's end of unit assessment on forces. Some really good answers, some really good attempts, and just want to spend a bit of time now going through and see if we can see what we can get from where we went wrong. I'm going to go to the majority of the questions. The best thing to do with these videos is to try and follow along, take some notes, and then once you've done that, go back over it again and see if you can then answer the question. So, first question talks about a diagram shows a boat pulling a water skier. It says the arrow represents the force on the water produced by the engine propeller. The force causes the boat to move. This was actually a very difficult question to start off with. And if you ever see a question that's about forces and it's asking you to explain, the first thing you should be thinking about is Newton's laws. In this case, we need to explain this using Newton's third law. Now, just to remind us, Newton's third law states that if there's a force from object A on object B, then there's a force from object B on object A. In this case, what are your two objects? You've got the water being pushed and you've got the engine propeller. So it tells you there's a force from the propeller force on the water, from the propeller. So what you've got to explain here is that if there is a force, this is the wording that's important here, from the propeller on the water to the left, this is where we bring in Newton's third law, there must be an equal but opposite force on the propeller from the water to the right. Really important that you've got your things there, the two objects, the propeller and the water, propeller and the water, and you've talked about the fact that there must be an equal but opposite force. For the next question, it was a calculate question. Now, as soon as you see the question with the command verb to calculate, the first thing you should think about is what equation do I need to use? Now, this is one of the equations that isn't given to you, and it's the acceleration is equal to the change in velocity divided by the time taken. So you then have to look at the numbers you've been given in the question. It's always a good idea to highlight the numbers you've been given to help you draw out that information from the question. So what's our change in velocity? It goes from 4 to 16. That must mean the change in velocity must be the difference between these, which is 12, and our time taken is 8. So you do your 12 divided by 8, and that will give you 1.5 meters per second squared. This next question is also a calculate question. So again, in the numbers and the command word, you can see that it's giving you the mass of the skier. It's asking for the resultant force. This is one of your key equations, yet again one you've got to remember. and that is F equals m times by a. Remember, Newton's second law says that if there's a resultant force on an object, it will accelerate. And this formula tells us the resultant force is equal to the mass times by the acceleration of the object. So we've got the equation, plug our numbers in. We do 68 multiplied by, in this case, our acceleration, what we've calculated here, times by 1.5. Substitute that in, and that gives you 102 newtons. It then asks you to talk about the force pulling the water skier forward. And we've worked out the resultant force on the skier. So we're looking at the skier here. Now, is the force pulling it forward going to be greater or less? We've got to think about what forces are acting on this skier. So we've got the force from a boat pulling the skier forward. Are there any other forces acting? At the moment, we're trying to drag the skier through the water. So there is going to be, to put the tension in the rope pulling it forward, there is going to be a force from the water causing a drag on the skier. So what that means is the force pulling the boat forward, pulling the skier forward, is going to have to be bigger than that drag. So the answer to this is greater than. And the reason why is so that it can overcome, so it can be bigger than the drag. So we can say here, to overcome drag or air resistance. Our next question is in a bit of a different context. So we're talking about stopping distance, thinking distance, and braking distance. First question is what is meant by the braking distance of a vehicle. This is one of the definitions that you've got to know off the top of your head. Keys in the words, braking distance, and this is the distance travelled while the vehicle is braking. Let's just recall where these definitions come from. If you're driving along the road and you see a hazard in front of you, there's and then you stop. There's two things that happen. There's the time it takes for you to react to seeing that hazard, and in that time you've travelled a distance. That's called your thinking distance. You then push the brakes on the car, and then the car comes to a stop. That second distance from which the car is braking is your braking distance. And it asks here, this is one of these common sense type questions, explain why the stopping distance of the car increases if the driver is very tired. Now, lots of you, when you answered this question, you missed out what tiredness affects in this situation, and it affects your reaction time. So to get the first mark, you've got to talk about tiredness increasing reaction time. You then need to say, what effect is that going to have? Well, if you've taken longer to react, in that time, your thinking distance increases. So I'm going to say here, therefore, thinking distance increases. And then linking it back to the question, we then say, as thinking distance increases, the stopping distance must therefore increase. Try and bring in key terms here where appropriate. So talk about it increasing your reaction time, and talk about that leading to an increase in your thinking distance. The next part of this question brings us on to an experiment to do with this situation. So it says applying the brakes with too much force can cause the car to skid. And it then gives you a fair bit of information. Bit of a hint here that may seem obvious. If you've got a question in the physics exam which gives you that much information, you're going to be asked to use it in the other question. So it will, in a bit of like a comprehension that you might do in English, the following questions will come back and rely on you having interpreted this information. So it says the distance a car skids depends on the friction between the road surface and the car's tyres. And it then goes on to describe this experiment. I suggest you pause the video here if you haven't given this a chance to read, so that you can have a look at it and then understand it in the next questions. It then asks in the first question, why is it important for the sled to be pulled at a constant speed? So it then gives you these three options. One thing as a background information about friction that's worth knowing is that it's hard to get something going than it is to keep it going in terms of friction. So once something's actually moving, the frictional force actually reduces slightly. So if you've got something that's, say, stationary on a table and you try and push it, as soon as that your force you're pushing it with overcomes friction, it will start moving. But then as soon as it starts moving, the friction drops. So the answer to this question is going to be the middle one. If the sled accelerates, the value for the constant of friction will be wrong. That's because the object will have started or changed speed. This next question is also thinking about how friction affects an object. So if the sled is pulled at an angle to the surface, calculate the value calculated for the friction constant would not be appropriate. So this friction constant is just about a measure of how much friction is acting. Now, you can think about this intuitively again. If you try and put your hand on the table and move it, you can slide it across the table quite easily. If you push your hand down and then try and drag it across the surface, it's not so easy to pull. And that's because the friction depends on the amount of downward force acting. Now think about what's happening in this situation. That pulling force is actually acting up slightly. So what that's going to do is going to reduce the contact force between the surface and the object. And that's the first point you need to make in answer. So it reduces the contact force between the surface and the object. And then we can say, therefore, what effect's that going to have on the friction? Well, if your contact force is less, it's much easier to slide across. So, therefore, the friction is reduced. This now brings us on to our final question. And this was actually the last topic that we've looked at as part of the distance learning we've been doing on this topic. And it's this idea of a skateboarder. You've got this idea that the skateboarder jumps off the skateboarder moves in one direction, the skateboard moves in the other. Explain using the idea of momentum why the skateboard moves backwards. As soon as you see this idea of momentum, we need to be thinking about the conservation of momentum. I was pleased to see that some of you mentioned that in your answer. So, to answer this in a logical order, we first need to talk about the conservation of momentum. What does conservation mean? It means that the momentum is kept the same. So, conservation of momentum, and we've got to say that we've got to show that we understand what the conservation of momentum is. So, the momentum before equals the momentum after. So our next point is, so what is the momentum before? It tells us here the skateboard is stationary at the moment the skateboarder jumps. What does that tell us about the momentum? Well, if something's stationary, it's got no momentum. So we can say before the total momentum is 0. And we're sort of coming up to our 2 out of 3 marks on this question. Before total momentum is 0, well, how can that be? How can it be that that's the same as after when they're both moving? And this links back to them moving in opposite directions. So, because the total momentum before is 0, that must mean afterwards the total momentum is 0. And it tells us that the skateboarder jumps forward. So we can say here that the skateboarder carries momentum in the forward direction, and therefore, for the total momentum to be 0, the skateboard must carry momentum in the opposite direction to cancel out the momentum that the skateboarder has carried with it. So, therefore, skateboard must carry momentum backwards. Quite often with this question, it's asked in completely different contexts. So sometimes it can be, why does a gun recoil when it's shot? Why does a cannon recoil when it's shot? It's all for, even though they're different contexts, they're for exactly the same reason. If the total momentum before is 0, and if one thing carries momentum in a forward direction, the other thing must carry momentum in a backwards direction to cancel out. So the total momentum after is 0, as well as the total momentum before. Finally then, it's now asking us to use this conservation of momentum in a calculation. This is what we practiced a couple of weeks ago before the test. I suggest if you got this question wrong, as well as you following through this working out with me, you also go back and look over those videos and work through those calculations again, because it's following the same process. The way I like to think about this is we have a before situation and we have an after situation. And remember, we don't want to spend lots of time drawing, we can just do blobs. So before, we've just got one stationary blob. That's the skateboarder and the skateboard. Afterwards, when you've got the skateboarder moving in one direction, and you've got the skateboard moving in the other. And then we label what we know once we've done those blobs. So do we know the mass of the skateboard and the skateboarder? It's given us here, so it would be 42 plus 1.8, which is 43.8 kilograms. Do we know the speed it's moving at? Do 0, stationary before, in the question up here. Now it says here, if the calculate the velocity at which the skateboard moves backwards. So we're calling that x. That's a thing we don't know. If the skateboarder jumps forwards at a velocity of 0.3 meters per second, so we can label that arrow 0.3 meters per second. And here we've got the mass of the skateboarder, which is 42 kilograms, and the mass of the skateboard, which is 1.8 kilograms. The main purpose of drawing these diagrams is to help you collect the information in the question. So once we've drawn the diagram, we then say momentum before equals momentum after. What's our total momentum before? We've said already, we said it in the previous question as well, the total momentum before is 0. So that's going to be equal to the momentum after. So remember, momentum is given the letter P and it's mass times by velocity. We've got the momentum of the skateboard, which is 1.8 times by x. We add that to the momentum of the skateboarder, which is 42 times by 0.3. So we then end up with, if I carry on working down here, we end up with 0 equals 1.8x, and then we can do the 42 times by the 0.3, which gives us plus 12.6, and then we rearrange that to make x the subject, which is our unknown. So to get x on its own, we've got to subtract 12.6 from both sides, and we've got to do the same thing to both sides. So minus 12.6 equals 1.8x. The last stage in that calculation, we want x on its own. At the moment, it's being times by 1.8. How do we get rid of that? We've got to do the opposite, which is divide by 1.8. So to get x, we've got to minus 12.6 divided by 1.8, and that gives us minus 7 meters per second. Why is it a minus sign? Does that mean we have to worry about having the wrong answer? Not in this case. It just tells us about the direction. The minus is telling us that skateboard is moving backwards. So in this case, velocity of the skateboard, minus 7 meters per second, units already there for you, and you'll get your 3 marks. So what I'd like everyone to do now, as I said at the beginning of the video, is to go back over your assessment. Once you've taken notes on all of this, have a go at reattempting the questions that you got wrong or didn't get full marks on, and see if there's anything that you still don't understand. And hopefully I'll see some of you in college next week.